Okay, so this lecture is separate from the other ones. It should be the third lecture, but I call it lecture 2 prime because I want to include a couple of problems that clarifies the previous knowledge about product rule and about factorials. So also important thing here is I want to explain once again the uniformity criterion which we used before, and you will see, I'll show you a problem which has two different answers, and we have to understand which answer is correct, and maybe both are incorrect, and which answer is really correct. Okay, let's start with the first problem. Problem 1. Okay, this problem we started when we learned the low plus minus 1 and arithmetic sequences. The problem is the following: how many two-digit integers are there? Okay. So that was one of the first problems we solved in our course, and I show you two different solutions. Okay, solution number 1. Of course, the answer will be the same, otherwise it doesn't make sense. Solution 1. Okay, so solution is the following. So let's write all the two-digit integers. The smallest integer is 10, next is 11, next is 12, then 13, 14, and so on. Okay, then 20, 21, 30, 31, so on. And finally you have 97, 98, and 99. So all the two-digit numbers are written here. How many of them? This is a question. And that question you have to solve based on our first chapter, our first part of the class, as follows, using the law plus minus 1. Okay, this law says the following: what is the length of this sequence? It means if you measure with a ruler, so what is the length? It's 99 minus 10. Which is 89. What is 89? 89 is the number of intervals or commas between the numbers. 89. If you want to find the total number of numbers, you have to add 1, because the number of numbers will be one more. So the number of two-digit. Okay, number of two-digit integers equals 89 plus 1, 90. So this is the answer. Okay, that answer we just learned from the beginning of our course. But now I use the multiplication rule, or the fundamental principle rule, and solve this as follows. Solution number 2. So what is the two-digit integer? How do we write integer? So we write the first digit and we use last digit, second digit, correct? This will be two-digit numbers. For example, 55 or 73 or 10. But 06 is not a two-digit integer, it's one digit. So therefore we can say that A is not 0. So what is the alphabet for the first digit? It's alphabet, I mean which digits can you use as a first digit. It's 1, 2, 3, and so up to 9. We have 9 possibilities. B can be any digit, 0, 1, 2, 1, 2, 3, and so on, also up to 9. But you see the difference is that digit 0 is in here. So second digit can be taken from this set, consisting of 10 characters. So we have 10 possibilities. So now the product rule tells that the total number is 9 times 10 is 90. And we got the same answer, but much simpler, much faster, and much more productive. Okay, do you like that second solution? Just in one second. Now let's solve another problem. And in this problem, let me just make some remark about this. So if I ask you how many 3-digit integers, if you write down, so the first 3-digit number is 100 and 101 and so on, and the last will be 991. So the same thing, you find the difference, it will be 899 plus 1, it will be 900. And if you have this solution, you have 3 digits, you have 3 possibilities. Letter A. So first digit is taken from 9 possibility, then 10, and then 10. So it will be 900. The same answers, all the time. But now I formulate the following problem. Okay, problem 2. Also, how many? So this is a standard question, starts with how many. How many 2-digit integers, okay, A, B, with B not equal to A are there. Okay. Before, for example, in this case, in the first case, we consider the numbers like 55 or 44, and now we have to remove them. And let us solve immediately using the fundamental principle. Okay, so let me just write first solution. Okay, I have 2 positions for the digits, A, B. So A is not 0. So we have 9 possibilities, like here, 9 possibilities. Then B now is taken from the alphabet 0 from 9, but if letter A is in here, then letter A from this alphabet mustn't be taken. It's not equal. So therefore B is not equal to A, and therefore instead of 10, we remove one of them. We don't know which one, it depends on what is your first digit, A. But you have all 9 possibilities. So total we have 81. So this answer is 81. But if you look at the uniformity criterion for multiple part tasks, it should be homogeneous. Let's solve. Let me show you second solution. Let me just write where is better to write. Okay, second solution. Okay, you have two possibilities. Okay, let's call the solution as follows. First A, I will use big A, and then B. In this case, I will consider solution small a and big B. It means that I start with B and then finish with A. Okay, so I start with B. So far there is no restrictions, yes? Okay, so we continue the previous problem. So the first problem was how many 2-digit integers are there, and we solved in 2 different ways. One way is to find the 89 plus 1 is 90. The other way is just A is not 0, we have 9 possibilities. For B, you have 10 possibilities, any digit is possible. And multiplication rule tells you the answer is 90, the same answer. Okay, now I solved problem 2. This time digits should be different, distinct. how many two-digit integers with different digits. First solution is that one. We start with letter A, so I write big A, and then we continue with B. So letter A has a restriction. A is not 0. So we have 9 possibilities, 1, 2, 3, up to 9. Letter B, okay, so digit B has would have 10 possibilities, but one possibility must be removed. Because B is not equal to A, so you have 9 possibilities. And 9 times 9 is 81, so this is the answer. But now I solve the same problem in a different way. I start with B, and then I finish with A, so which is reflected as follows: big B and small a. So we have 10 possibilities. For B, no restrictions, okay, so any digit could happen. So let me just write big B, and let's say it's big A. And now I go to first digit, so in that direction. In this direction, so what do I have? First of all, it's not 0, right, as in previous one. But also, because B is not equal to A, it means that A is not equal to B. So therefore, A is not equal to B. And we just cannot use 0 and B used on the previous step. So we have only 8, so we have therefore 8 possibilities. Okay, and the product rule tells us that the answer is 8. Okay, what's going on? You see two different answers. Okay, which one is correct? Maybe both of them are incorrect. So first check which one is correct and then find a mistake in the incorrect solution. Because one of the solutions, at least one, maybe that is incorrect and this correct, or maybe this is incorrect, that correct, maybe both of them are incorrect. Both of them couldn't be correct all together, simultaneously. So, so what do we have? We have, let's check this as follows, check. Okay, check. We have 90 two-digit integers, right, which we found in the previous problem, from 10 to 99. And we have to remove those, of those 90, we have to remove the ones which have equal digits, right? So what numbers have equal digits? 11, 22, 33, 44, 55, 66, 77, 88, and 99. How many? 4, 4, 8, 9. So, okay, total is 9. Okay, so it's 9. 9. So 90 minus 9 is 81. Okay, now we know that the correct answer is 81 is correct answer, and that answer is incorrect. But our logic looks like correct. So let me repeat once again. What is the idea? Idea is just choose a plan. Okay, meaning that I have to choose one digit and then go to another digit. So in here I use the first digit and then went to the second digit. So 9 possibilities for the first, 9 possibilities for the second, because B is not equal to A. And I got 81 found in here. This one I take first digit, second digit, and no restrictions. I could take 0 from 0 to 9, so 10 possibilities. And second one, so the first digit when I go backwards is not 0, first of all the time, and also is not B. So I have 8 possibilities, which is 10 minus 2. So I have 80. So what's wrong with that? So the matter is that the matter is that 0 is not here, and 0 is there for B. So I have to consider 0 separately. You see, what does the uniformity criterion say? It says that if I take one task and then I make second task, then the number of ways to make second task does not depend on the number of ways to choose the first task. The tasks can depend on each other, but the number of ways doesn't depend. This is what happened in here. If you go from B to A, you have 10 possibilities and 9 possibilities for A if I go from B to A. So this 9 does not depend on 10. But in this case, the number of choices for A is different. So you have to consider two disjoint cases. Let me just write 2 disjoint cases. B equals 0 and B is not equal to 0. Okay, disjoint means that either this one or that one, no intersection. Now, if B is 0, then for A, what A could be? A could be any number. A belongs to any number from 1 to 9. And in this case, of course, if B is 0 and A is any of those numbers, definitely A is not B. So therefore you have all these A's work. Okay? So how many possibilities you have? For B equals 0, it's one possibility. Okay, that possibility we consider. So we have 1, okay, for B equals 0 times how many possibilities for A? 9. So therefore here we have 9 possibilities in the first case. Is it clear? So first, if B equals 0, 1 possibility for B, and then how many possibilities for A? Could be 1, 2, 3, up to 9. 9 possibilities, so the answer is 9. Second case, B is not 0. So therefore, what is B? B belongs to the set from 1, 2, and so on up to 9. And A, after that we go to A, which is not equal to B, right? So for B you have 9 possibilities, 9 ways. But for B, for A now, you have how many possibilities? If I choose some B here, then A is not equal to B. So therefore this possibility I have to remove. And out of 9, I have only 8. So therefore you have total now, 9 ways to choose. Okay, to choose B, and 8 ways to choose A. Total we have 72. So therefore, if B equals 0, I have separately 9 possibilities. If B is not 0, then I have 72 possibilities. Now add them up, and you get 72 plus 9, it will be the same answer, 81. Okay, so this example demonstrates the uniformity criterion you see for multiple part tasks. Because your choice of plan, how to solve problems, so what you have to do first, what you have to do second, and so on, you have to split onto disjoint cases. Once again, if B equals 0, then A, because A cannot be equal to 0 all the time, therefore this case is separate. If B equals 0, then A belongs to 1 to 9, and therefore automatically is not equal to B. So it follows, logically it follows that A is not equal to B, and that's why all the cases should be considered. One case for B equals 0, and 9 cases for A from 1 to 9. But if B is not 0, then you choose some B here, and that B is in the set for A. because A is not 0 anymore. So it's only from 9 possibilities. So, and now you have to subtract 1. So this 8 is 9 minus 1. So mistake was in here. Instead of finding 10 minus 2 to get, to get 8, we have to subtract 1 from 9. 9 possibilities for A, one of which is not equal to B. So we have 72 separate possibilities. Okay, you have 9 possibilities here, 72 possibilities, and altogether it will be 81, not 80. So be very careful and solve the problem of that kind using the restrictions, recommendation. If you solve some combinatorial problem of that kind, choose first a step, the first step, or steps, which have, okay, one step, which has the most number of restrictions. So like here, A is not 0, here, first step, A is not 0, it's a restriction, and for B there is no restriction. So you have 9, and this you have 10. Here you have not 0, so 9, and then B is not equal to 8. Second restriction is, will be 9, so 81. Okay. Another check which shows the second solution can be shown in the on the table. So let's consider the table. So first digit A and second digit B. B could be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. A can be only 1, 2, 3, 4, 5, 6, 7, 8, and 9. I will not draw the whole table, but I want to show you. Okay, please draw the lines. Okay, but you show that if you use A, 1, 0, okay, 10, 20, 30, 40, 50, 60, 70, 80, 90, there are those 9 cases which I considered here, so 9 cases. And all the other cases, what I have to do? I have to remove, okay, so 11, then 22, then 33, 44, 55, 66, 77, 88, and then 99. So those I have to remove, and what's left over here and here will be my number. So what is that? It's 9, the same thing, 9, and here you have, so if you count total, it will be 90. Okay, I just repeat what I did before, but using the table. 90 are all together, and then minus this kind of diagonal if you remove the first column. Minus how many of them? Minus 9. So the answer is 81. Did I get this 81 some? So I got the 81 9 times 9. 72 plus 9. And also 90 minus 9 is 81, the same thing. So this is the third check. Okay, the third check. Okay. Now let me consider the following the following important problem. Okay, this problem 2, problem 1, problem 2. And now let me go. Let's go to the problem 3. How many? Okay, the standard. So problem 3. So starts with how many, and now I'll tell you how many of what. How many different subsets does have a set with n elements. Okay, that question we considered in the previous part, in the set theory part, and we know that the number of such subsets, we know the answer. The answer is 2 to the n subsets, okay, including empty subset and how do we call how many does have a set? Call it A, and set A. So 2 to the power n, power of 2. Okay, how come? How to explain this result, this answer? It turns out that a subset could be could be considered as a string of zeros and ones. Okay, you can code it. So each subset has a code. Okay, each subset of A has a code, and this code is a string of zeros and ones of length n. Has a code. It's a string of, this is how come. So let me show you on some examples. So suppose we have a set, suppose n equals 4. And suppose you have set A consists of letters A, B, C, and D. Okay, what are the subsets? You have, let me just write down what are subsets. So first subset is, empty subset is 0 subset. Okay? And there is only one. Only one such a subset, right? Only one. Now consider subsets A, okay, B, C, and D. Let me just omit the parentheses, curly parentheses, which must be used when you write the set itself. But I omit this. You have A, B, C, D. So how many of them? You have 4. Next you have double sets. You have AB, AC, AD, BC, BD, and CD. So you have 6 of them. So we just write, we just find in the listing form all possible subsets. Next is triple one. ABC, ABD, BCD, oh no, sorry, ACD first, and then BCD, and that's it. So we have 4 again. Next you take the whole set, which is ABCD, so equals A, so it's 1 of them. Okay, so we know exactly how many subsets of each type you have. One subset has no elements, 4 has exactly 1, 6 has exactly 2, then 3, and then 4. And so the numbers are and this number. So if you add them up, 4 plus 6 plus 4 plus 1, you get a very interesting number, which is, please tell me what is that?
16?
Yes, 16. What is that? 2 to the power 4. Exactly what's written here. N elements, and so it will be 2 to the power n. How come? Why the sum is equal to 2 to the n? So where did 2 to the n come from? Okay, now I explain to you using the basic principle of combinatorics, of counting method. But to do that, I want to code each subset. And I do this as follows. So A, B, C, D, I write the following table. And let me just write for each set. I don't want to write all the sets, but I will show you some examples. Let me show you empty set. Okay, then I show you, say, set A, set B, okay, and then let me just miss, say, set ACD, and so what is ACD? Maybe double. So first AC, and then maybe ABD, and the final one says ABCD. Okay, I make the following code. For each element written on the top, okay, so in here, I will just write I just write 0 if this element does not belong to this set, and write 1 if it belongs. Okay, start with empty set. Does A belong to empty set? Tell me please.
No.
No. What should I write?
0.
0. How about B?
0.
0, 0. So we have the code 0, 0, 0. It's empty set. Okay. Now for A, does A belong to this set? Okay. This time I'll just write a set like this. Does A belong to this set? It's an element, so it's 1. I write belongs. B does not belong to 0, 0, 0. Right? How about B? A does not belong, B belongs, C does not belong, D does not belong. Okay, so 0, 1, 0. How about AC? A belongs, C belongs, but B and D do not. You have this code. How about ABD? A belongs, B belongs, D belongs. So I write zeros, so ones, and then 1, 0. And about ABCD is 1, 1, 1, 1. And so on. So actually this is a part of the table I have to write. Okay, you got it, right? So for example, if I write, say, so for example, ABC. What is the code of ABC? A belongs, B belongs, C belongs, D does not. Oh, sorry. I have to write this as a ordered, okay. ABC is a set. Order is not important, but that one is important. It's called vector. So let me just write this is set, and that one is called vector. Okay, it's order. Okay, order is important. Okay, so you see that every single subset corresponds to a string of zeros and ones, right? Understand that? Okay, so how many positions do we have? 1, 2, 3, 4. For A, B, C, D. Now, and I want to write the whole table. What should I do? How many possibilities are for A? What A could be? A could be either 1 or 2. So let me just write A belongs to the set 0 or 1. This is how I code. 2 possibilities, correct? How many possibilities for B? 2 possibilities. For C, 2 possibilities. And for D is also 2 possibilities. So therefore I have to multiply, and I get to the power 2 to the power 4. And if I have n of those, I again have 2 possibilities, 2 possibilities, 2 possibilities for A, B, C, whatever. Let me just write letters. A, B, C, D, E, F, G. I have 2 possibilities for each. So either 0 or 1. And so total will be how many here? 3, 6, 7. 2 to the power 7. It's what? 2, 6. 128. 128. The question is, But if I count in that in different way, I'll get this. I have to add the number of subsets for each category, and then add them up, and so the sum will be definitely 2 to the power n. You understand it? I showed some examples. Here is n equals 4, and that 4 is in here, and here is n equals 7, and that's why 7 is here. Got it? If I have n positions, so I have n subsets. Okay? Okay, so we know that. And question is how to arrange these subsets. Let me show you a simple example. Okay, suppose you start with 0. On the first position, what could happen? 0 or 1, right? If I have only one letter. So if I have a set, if I have set A consisting of one letter, so which subsets I have? Empty set or set A itself, right? So it will be 2 of them. 2 to the power 1. One element, n equals 1. So 2 to the power 1, which is 2. And there are 2 of them. So 0 or 1 for A. Now I go to B. What could happen? I just double this 0, and I can write 0, 0 or 0, 1. I can double 1 and write 1, 0 or 1, 1. And I have 4 possibilities. Okay? And now this one corresponds to empty set. This corresponds to the set B. This corresponds to the set A. And this corresponds to the set AB. Got it? If I have A and B. Now, what I have to do if I have to have 3 letters, A, B, and C. For A, I have either 0 or 1. For B, I have either 0 or 1, but there are two times. So if A is 0, then for B I have 0 or 1. For if A is 1, I have also 0 or 1. How to get C? How to enroll C here? I just rewrote this one, and I rewrote this one. And I will do this as follows. I will just write 0 here, and this 1, and I write 0 here, and this 1. So I take the previous possibilities and double, and so I just split. I have this one and the same here. If I put 2 zeros here, it will be extension for as zeros, and that one extension with 1. So the 3 here, okay, how many I get? Of course I get 1, 2, 3, 4, total is 8, 2 to the power 3. 2 to the power 3 is 8. So what is the idea? So here, if we draw the tree, I have either 0 or 1. Okay, so next I extend again, either 0 or 1. Likewise here, 0 or 1. If I extend here, it will be 0 or 1. This also 0 or 1. 0, 1. And finally also 0 or 1. And now after that I just travel from the root, from the beginning, to the leaves. And I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, got it? This is just pure combinatorics, but it turns out that this beautiful idea with the extension gives to some interesting geometric object. Okay, so let me show it to you. So in the beginning I had 0 and I had 1. Okay, so 0 and 1. Then I just double 0, write 0 here and 1 here. And then I write 0 here and just write 0 here 0, 1 here. Here I write, so it starts from 0, now it starts from 1. So it will be 0 and 1. I do the same thing, but now I draw the points. So if I connect them, I will get a square. Before I had segment, now I have square. What should I do after that? I have to double it. So let me just draw a square again and reroll it here. So 0, 1, 0, 0, 1, 1, 1, 0. And then I just write everywhere zeros on the right side. Okay, 0, 0. And here I just write everywhere 1 as the third digit. And I have a new square. And if I connect those, what I'll get? Here, what I'll get? It looks like cube. It's a three-dimensional cube. Okay, so and those ones and zeros are the coordinates of the vertices. 3 coordinates, x, y, z, and each one is 1, 0, either 1 or 0. So usually it's drawn as follows. Okay, you draw this one, like that one. So you have the axis x, y, and z. So here you just write 0, 0, 0. This is 1, 0, 0. This is 0, 1, 0. And then here is, okay, the final, this vertex will be 1, 1, 1. Okay, so that one is 1, 0, 1. And this one 0, 1, 1. And that one is 0, 0, 1. Okay, so all the coordinates, but actually, what do you have? You have a cube. No, it's a little bit deformed cube, but that cube also could be drawn as follows, as kids draw, but it's very important for mathematics. So you can draw this way and write 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0. Inside that cube you can draw a small cube, and you just write 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, and then you connect. Okay, so it's cube. If you look from the top, and if you take the face, the upper face, and shrink it, okay, then you'll have a cube. So this is the same cube. But we should, so this is n equals 3. Okay, it's three-dimensional cube. And it has 2 to the power 3, which is 8 vertices. Let's do the following. If we go from n equals 3 to n equals 4, what we have to do as follows. We have to take that picture. Let me just draw this picture. Okay, that one. Okay, shift it. Okay, draw once again. Okay, shift it. And then connect. Let me just use this different color. Okay, connect the respective edges. So this one and that, this and that. Okay, that one and this one, that one. Here is this one. That one is in here. Finally, that is that one. So it will be messy, but okay. Okay, so what you have? Now you have n equals 4, 2 to the power 4 is 16, 16 vertices, and what's drawn in here is a 4-dimensional cube. 4-dimensional cube. And four-dimensional cube has not only two-dimensional faces like that cube had 1, 2, 3, 4, 5, 6, but also three-dimensional faces. This is the bottom, and this is the top summit, and also could be different one. But you see, everything just came from this multiplication rule: 2 times 2 times 2, and so on. This four-dimensional cube, if it's drawn on the from children point of view, can be constructed in our space as follows. Actually, what is that? We have four-dimensional cube. It means you have four different dimensions. Here we have 3, x, y, and z. The fourth dimension is time. And if you have four-dimensional cube, means you take a cube, and then shift it along the time. And now, if you stop, say, in 1 second, so in that direction, you have time. And in these 3 directions, you have x, y, z. So three-dimensional space, and 1 dimension is time. Now we have four-dimensional cube, and this cube, you see, that face, this is the bottom, and this is the top face. But face itself is a cube again. Before, face was a square, and now you just cube. Okay, so it could be drawn as follows, like children drew three-dimensional cube. It's projection on the plane. This is also projection of four-dimensional space, first into three-dimensional space, and from three-dimensional space on the blackboard in two-dimensional. And you have that picture. But if you want to show in 3 dimensions, you have to draw this as follows. Okay, this will be one face. It will be bottom. And now the top face will be smaller one. It will be shrink in all the directions, and you have to draw this as follows. Okay, so you have to draw a small cube in here. It will be a face. And then you have to connect the respective vertices, this and that and that. So this one, that will be connected with this one. Now here is connected with that one. This with that, and also here. And now you have, so this one, okay, that big face is the bottom, three-dimensional face. And that one, this cube, is top face. Okay, three-dimensional face. And by the way, so look at the following picture. So this one, okay, like this, like that one. Okay, here kind of truncated pyramid. Okay, this one. Well, this truncated pyramid is also a cube, but deformed. It's a different face. It's a different face of the four-dimensional cube. So this one, also likewise, you have that one. You have to connect. You have this one also on the top. That face. There's many different faces. If you want to construct five-dimensional case, so you have to take this picture, shift it, and then connect respective sides. From a combinatorial point of view, you take these numbers, okay, double them, and then write zeros on the right side of all the coordinates, called coordinates. You write zeros everywhere here in all the vertices, and once do the same for the duplicate. You have to write once in the end, and then connect, and you'll get five-dimensional cube, and so on. So therefore, 2 to the power n subsets correspond to 2 to the n vertices of n-dimensional cube. Okay, our course is called mathematical ideas. And I show you a big idea, starting from sets, going to the different combinatorics, the product rule. And after that to geometry, which gives you multidimensional cube. And you see, I involved here one more direction, which is time. If you involve that, you'll be very close to the Einstein relativistic theory. Okay, so in four-dimensional space, it's called four-dimensional space-time. And maybe you've heard about that, it's just a part of physics, but actually it's a part of mathematics, and this is how it could be explained from simple point of view. So this is how it rises from nothing, from empty set, in a sense. Okay, so and the last problem which I want to consider in this part is also a problem with some restrictions, and I want to show you how fast you can find the answers. Okay, let me erase again this one. Start problem 4. Okay, how many different ways can you arrange that one, and so here this problem will consist of several items. Okay, how many? So the first one is how many paths go from A to C. Now let me just draw. You have points A, B, C, and so you have 4 rows here, 4 rows here, and this you have maybe to D. So this one you have 3, and from C to D, okay, 4, 5, 6, and this is D. Let me do the following. I will formulate the problem and then solve it immediately, instead of writing all the questions and solve separately. So how many paths go from A to D? You can go, for example, this way. Take one route is as follows. This one, that one, and this one. Or I can use that one, and now I use another one. You see there are many of them. How many? So you just you drive your car from city A to city D, and here you have possibilities here 4, 3, and 6. So the answer is very simple. You have you have 3 possibilities. So you mean 3 choices, right? So each time you have 4 possibilities for the first one, 3 possibilities for the second, and 6. So, and all of them are independent. Okay, so that's important. So you have 12 times 6 is 72 paths. Got it? Correct? Okay, good. Second problem. How many? Okay, so license places, how's it called? License
plate?
Plates, yes. License plates. Okay, so what is license plate? So it consists of digits, right, and letters, right? So consider, okay, so 3 letters. So here is, say, letters in the beginning, letters, and then 4, and this one is digits. Okay, so how many? Okay, if there is no restrictions. So on the first position you can use 26, one of the 26, A, B, C, D up to Z, then independently 26 for the other, then 26 for this one, but for digits you have 10, 10, and 10. And then you have to multiply. So total answer will be 26 multiplied 3 times to itself, so 26 to the power 3 times 10 to the power 3. Okay, so 26 to the power 3, I cannot calculate in mind. Okay, let me calculate. Okay, 26 cubed. Okay, 17. So this is the answer actually. 17, 576, and then we have to write 3 zeros. Okay, so many license plates, 17 million. Okay, this one I consider letters and digits. First letter, then digits, no restrictions. But suppose I want to, I can permute them, right? So if I use the previous problem, okay, please look in here. So the word initially. So what is the number of different different possibilities here? So letters are taken from the alphabet A, B, C, and so on up to Z. Okay, and each one in that case, right? All of them are distinguishable. Okay, so and here, okay, how many ways I can permute those ones? Okay, so there, I will not maybe consider it much more complicated. I want to show the simplest one. So I want to say that if you take, for example, exchange digits and positions and letters, then it will be some other 26 to the power 3 times 10 to the 3, but it will be different ones. So you have to add to the previous ones. What I want to say that I consider a special case. First letters, then digits, and no restrictions. But suppose I have, okay, the same problem as before, C, also license plates, but now restrictions is as follows. Okay, so these are first letter cannot be X, Y, Z. Okay, second one cannot be, so M not equal N, K, and P. Okay, so third one is not could be equal only A, B, or C. So here we have not equal, this is equal. Okay, now for this one is the number divisible by 5. Okay, that number is even. And so how many? 1, 2, 3, so 2 more. Okay. Okay, that number, okay, suppose I want to make license plate, which must be written 7, okay, which must be written, yes, okay, 7, and only one equals 7, and the last one say divisible, not divisible, how to say, okay, 7, no, let me start, 8 or 9. Okay, suppose like that. It's a pretty tough problem on frozen letters, but it's simple if you understand what you have to do. So first one, first letter, okay, this letter, not cannot be X, Y, Z. So its alphabet has 26 letters, but if you exclude X, Y, Z, you have 26 minus 3, right? So many possibilities. Now, in the second one, independently, I exclude N, K, and P. So I have to take 26 minus 4. The third one, either A or B or C. So how many possibilities? Either A, 1 possibility, 2 or 3. So you have 3, exactly 3. How many numbers? So digit is divisible by 5. What could it be? It's either 5, so So either 0 or 5. You have two possibilities, right? So therefore 2. Now this one could be even digit. Okay, let me just write. So this one is digit, and this is also digit, and this is letter. So even digit. What even digit? So it could be 0, 2, 4, 6, or 8. Correct? How many possibilities? 1, 2, 3, 4, 5. 5 possibilities. Okay, less digit. Okay, so this one must be 7. Okay, the driver wants to have 7. So I take only one possibility, because it's exactly equal to 7, nothing else. This is 8 or 9. So we have two possibilities, either 8 or 9, right? And now I have to multiply all those. And so what's the answer? 23, let me just write up here. 23 times 22 times, let's just rewrite all of those. 3 times 2 times 5, and times 2 again. So 5 times 2 is 10, 3 times 2 is 6, and 23 times 20, okay. Anyway, we have to calculate, use calculator. Okay, so 23 times 22 times 6 and times 10. Okay, so 30,360. Okay, do you like the questions? Okay, I want to show simple questions, so for application of the product rule, because that kind of problems will be in the test or in the quiz. Okay, next part is D. Okay, 4-digit integers. Okay, integers belonging to the set 1, 3, 5, 7, and 9, all odd. And let's just write D1. Okay, all 4 digits are distinct. So how many such integers are there? Okay, so let's look. 1, 2, 3, 4. 4 positions, right? How many? So start with number 1, first position. So how many possibilities? Let's just write first, okay, second, third, and fourth. Start with number 1. How many possibilities for first digit? How many? Please tell me.
5.
5, yes. 1, 2, 3, 4, 5. Yes, 5. Okay, now for the second, distinct. So it cannot be, we don't know which one you use, for example, 9. But if you choose 9, then second digit is not 9. How many are left over?
4.
4. For the third position, okay, 2 of them are chosen, and third is not equal to that, so therefore 3. And for the fourth is 2. So it will be 4, 5 times 4 times 3 times 2. And you see, it's interesting. So the answer is, if you multiply by 1, nothing will be changed, right? So the answer is 5 factorial. And the answer is 120. Okay, all the 4 digits are distinct. And now, what is this tricky but very simple question? All 4 digits are equal. Then, what do we have? 1, 2, 3, 4. Okay, first digit, second digit, third digit, and fourth digit. So for the first position, how many possibilities? for the first?
5.
5, yes. For the second?
1.
Yes, 1. If you put here as A, this also must be A. 1 for the third, 1 for the fourth, also 1. The answer is only 5. And it's clear which ones. 1, 1, 1, 1, 1, 3, 3, 3, 3, and so on, 5, 5, 5, 5, 7, 7, 7, 9, 9, 9. Exactly 5 of them. Okay. Maybe okay, D3. Okay. Let me try first digit. So the same question. 4 digits, integers belong to this one. First digit equals second digit. Okay, and first and third digit equals fourth digit. Okay, end. So this important end. Okay, let's count again. 1, 2, 3, 4. Let me call them A, B, C, D. Okay, instead of first and so on. So A, how many possibilities? 5. How many for B?
1.
1. 1. For C? No restrictions. Also 5, right? Any of those could be chosen, right? And for D is also 1. So you multiply, you get 25. 25 so exactly. Like, say A, and this will be CC. And whatever you can put, you'll get 25. Okay, now D4, maybe the last in the sequence. Okay, the same thing. First equals second. And now or, okay, or third equals fourth. Okay, so you see this is a different one. Okay, so let's look. So AB, CD. Okay, first equals second. So the same 5 possibilities for A, 1 possibilities for B. Right? Okay, when I say or, it means either this or that or both. Okay, so let's look. A has 5 possibilities and B equals A. But now, okay, when I say or, it doesn't mean that for this choice, C and D must be equal. They could be different. So we have 5 possibilities here, independently on those ones, and 5 possibilities here, which indicates if they're independent. So we have so many possibilities, which is 5 to the power 3, 125 cases. So we consider case when A equals B. So case 1, A equals B. And C and D, any. C and D, any. Now case 2, A, B are any. And C equals D. So in this case you have 5 possibilities, and this one also 5, and this you have 1. And the same answer, 125. And finally you have case 3. Case 3, when A equals B, and, okay, simultaneously, and C equals D. Now in that case, we just considered in the D3. It's D3. So how many possibilities? We got 25. Okay, let me circle the answers. And you see all the cases are disjoint. If they are disjoint, we have to add them up. And then we'll find total number of cases. So it will be 125 plus 125 and plus 25. So it's, what is that? It's 250, 275. 275 for integers. Okay? You got it, right? So therefore, this is important thing. So and means simultaneous, but this and that. So 5 and 1, and this is 5 and 1, and then multiply. And if you have or, you have to consider different cases, okay, and after that disjoint cases, and add them up together. And the final problem which I want to consider in this part, and maybe we'll finish for today, is the number of divisors. Okay, so this number what? A, B, C, D, number E. Okay, so question, how many divisors does 360 have? How many divisors does 360 have? Okay. Divisor is what? Divisors, let me try. Divisors, set of divisors consists of the following. 1, 2, so if it's divisible by that, it's a divisor. 1, 2, 3, 4, 5, 6, 7 is not. 8 is here, 9 is here, 10 is here, and so on. And the last one will be 360. Okay, how many divisors? So now let's look. First of all, what is 360? So first represent is a product of prime factors. It's actually 2 times 2 times 2 times 3 times 3 and times 5, okay? Which is equal to 2 to the power 3 times 3 to the power 2 and times 5 to the power 1. Okay, so we have 3 of those, 2 of those, and 1 of those. So therefore, okay, this is the given number. Now, what is a divisor? D. D. If it's a divisor, therefore, it must contain at least one of these prime factors. Or maybe doesn't contain, but it cannot contain something else. So therefore, it could be considered as follows: 2 to the power x, okay, times 2 to the power y, and times 2 to the power z. And question is, so now if you change x, y, and z, so let's look what happens with x. X could be what? Could be, if you write 0, it will be 2 to the 0 will be 1. So it could be 0, in which case 2 is not here. Or could be 1, or could be 2, or could be 3. No more than 3, because it's divisible, it's 2 to the power 3. So x, let me just write, belongs to this set. Y could be either 0, okay, or 1, or 2 at most. And finally, z belongs to the set, it could be either 5 to the 0, which is 0, or just 1. 5 to the 1. So this corresponds, let me just write 3. So 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Okay, here we have 3 to the 0, 3 to the 1, and 3 to the 2. And that one could be 5 to the 0, which is 1, or 5 to the first, which is 5. Okay, so how to solve this problem? You have 3 positions for x, y, and z. How many possibilities for x? 1, 2, 3, 4. 4. How many possibilities for y? 1, 2, 3. How many possibilities for z? Is 2. So if you multiply, by the way, so if you multiply by 1, you'll get 4 factorial. 4 factorial, you can write 24. 24 different divisors. And all the divisors can be wrote in this case, in this way. So, for example, let me pick something. So let me show some divisors. Okay, divisor, say 1. So suppose I pick from here 2. Okay, 2 squared. From here I also pick, so suppose 1, 3 to the first, and from the second one I pick nothing. Okay, 5 to the 0. So what do I have? I have 4 times 3, 12. 12 is a divisor. Or, for example, if I take d2 equals 2 to the power 3, suppose I take 3 from here, 1 from here, 3 to the first, and 1 from here. 3, 1, 1. So what do I have? 8 times 15. 40, 120. Oh, I see this big. So it's another one. And you see, if you write 2 to the x, y to the y to the z, and plug in, so pick something in here, something in here, something in there, and you find the divisor, 2 and 24 of them. Okay, so actually I wrote all of those. So draw the table. Let me just show the table. Is it okay? Do you see it? So it's and wrote the table changing x, y, and z. And so this table. Once I multiply those, I got all the divisors as numbers, and after that I put them in the increasing order. So 1, 2, 3, 4, 5, 6, then 8, 9, 10, 11, not 12, 13, not 14, not 15, 16, and so on. And all of those, all the 24 are in here. Okay. Okay, so I think that I considered so the important chapter 1 and 2, so with the factorials and what is the most important, the product rule. This is the most important. And what's left over is chapter 3, chapter 4, and chapter 5. Okay, in chapter 3, it's counting methods. Okay, so it involves permutations and combinations, and also problems involving not and or. Actually, we consider some or here, and permutations and combinations we also considered a little bit. Okay, so when we used marbles and number of permutations, combinations, but actually it requires once again consideration. Okay, and finally, chapter 4, it's Pascal's triangle. Pascal's triangle explains, okay, I erased here, but explains why 1 plus 4 plus 6 plus 4 plus 1 equals the power of 2 to the power of 4. Okay, that explains the number of different subsets. It's very beautiful, Pascal's triangle. And finally, chapter 10, chapter 10 but section 5, problems involving not and or. And in a sense, we already did it. Okay, so it's, okay, in a sense, okay, we solved such problem. Maybe we'll consider a little bit more kind of, you have a deck of 52 cards, and then you choose 5 cards, and what is the number of ways to choose 3 red cards and 3 cards of diamonds, say. No, so what is black, how's it called? I forgot.
Spades or clubs?
Yes, spades or clubs, okay, something like that. So the number of ways to do that. Okay, so we finish for today.